Kia ora and welcome to question 1 of the 2011 Scholl Calc exam. This question's got 3 parts in it. We've got an inequality, we've got some random 3D solid that's made up of different types of triangles, and we're going to find a minimum, so it's an optimization question there, and we've got a differential equation. So the first question here is actually quite a stink start to the exam. They don't often do this, but question 1A usually is the more reasonable, ease you into the exam kind of thing, but this definitely doesn't. It's very easy to get this wrong without realizing it. Okay, we're solving an inequality. The first thing to realize when you solve inequalities is multiplying through by a denominator, multiplying or dividing both sides of an inequality works, but you have to be careful that you're not multiplying or dividing by a negative, because when it is negative, and the inequality will flip around. So I could do a case-by-case kind of thing with this and consider 2 cases. If 2e to the x minus 1 is greater than 0, and that's going to be true if e to the x is greater than 1/2, or x is greater than log of 1/2, then I just multiply through. I don't have to worry about the inequality changing. So ae to the x is less than 2e to the x minus 1, and then solving here for x, we rearrange it first. Divide both sides, but alas, we've got another problem here, because we need to know what happens when we divide by 2 minus a. So it's kind of like a subcase. If a is bigger than 2, what happens? We're going to have 1 is less than a negative number. No solutions. That's just a contradiction. If a is equal to 2, then we're going to have 1 is less than 0. No solutions. So it's actually as a is greater than or equal to 2 doesn't work. But if a is less than 2, then it does work for this, but we're going to be dividing by a positive quantity, and therefore we've got 1 over 2 minus a is less than e to the x, or x is bigger than log of 1 over 2 minus a. Now we have to put the solution to this case together with its original condition. We had a condition here that x had to be bigger than log of 1/2. Note that log of 1/2 is a negative number. The log graph, if we're making a graph here, the log graph or the natural log graph looks like that. And we're saying that we need to be bigger than log of 1/2, or 1/2 is actually in here. So x is bigger than log of 1/2, meaning that x has to be bigger than that, whatever this dude is. And then we're saying that the answer to the problem is x is greater than log of 1 over 2 minus a, but we're saying that a has got to be less than 2 for this. So because a is less than 2, did we get told that a was a positive constant? We did. That's helpful. A isn't just less than 2, it is between... What happens if it's negative? If a was a negative constant, would we have a bit of a problem? I'll think about that in a sec, but I think it means that the inequality doesn't work. Okay, so if a is between 0 and 2, then log of 1 over 2 minus a, we're going to be taking away a positive number, so we're going to get to 1 over, like for example, if a is equal to 1, then we've got log of 1. If a was equal to 0.5, we've got log of 1 over 1.5. And so we need to think about what we get there and what direction this inequality is in. We're actually going to be greater than log of 1/2. okay, because we're going to be dividing by a number smaller than 2, which means when we do that, we're going to be getting a bigger number inside the log, and the log is an increasing function. So our original condition is that x had to be bigger than log 1/2, and our final condition is saying that x has to be bigger than log of 1/2 minus a, which means that this here is satisfied. That's the answer to this case. X has got to be bigger than both of those things, but it's already bigger than log 1/2 if it's bigger than log of 1/2 minus a. X is bigger than log of 1/2 satisfies both cases, and if a is between 0 and 2. Okay, the other case which we needed to consider was if the original denominator was negative, and that would be if x is less than log of 1/2. Okay, the only thing that's going to change in the solving is that the inequality will flip around, so we'll end up having solving this. Now, if a is bigger than 2, then we've got a negative on the right hand side because e to the x is always positive, and a negative is always less than 1. So if a is less than 2, x is any number, but hold up, it can't be any number, it has to be less than log 1/2. So our answer is the original condition. We've restricted the x values to just looking at less than log 1/2. We've come out and said, hey, x can be anything provided it satisfies the original conditions. Now what about if a is between 0 and 2? If a, apologies. I meant a is bigger than 2, because we would have 2 minus something that's bigger than 2, a negative number. What happens if, for this particular case, if a is between 0 and 2? Well, then we're dividing there by a positive number, so the inequality doesn't flip around, and we're saying that x is less than log of 1/2 minus a. Oh, by the way, I can log both sides of an inequality without worrying about the sign change, because it's an increasing function, as I show up here on the graph, that if I take two x values, or like an x value and a y value, where x is less than y, the log of x is less than the log of y. The order of the inequality stays. Okay, so for this particular case, does it even work? I've got to start off with x is less than log 1/2, and then my answer comes out that x needs to be also less than log of 1/2 minus a, where a is between 0 and 2. Well, again using this logic here, log of 1/2 is less than log of 1/2 minus a. So if our original condition for this case says x is going to be less than log 1/2, it is already less than log of 1/2 minus a. The solution doesn't provide any further restrictions, so our answer in this case is actually the original condition. Okay, so to summarize, because it needs to be really clear what our solution is. If a is between 0 and 2, then x is bigger than log of 1/2 minus a. And if, that's only if a is between 0 and 2. Whereas if a is greater than 0, any positive number, then x is less than log 1/2. And that's because that second case had it worked for both greater than 2 and between 0 and 2, and it came to the same original condition being the solution to the problem. Okay, part B. Definitely a lot easier. We've got a 3D solid made up of two types of triangles, and the areas of the triangles can be calculated using these formulas. Find the value of k which minimises the total surface area, and show this value gives a minimum. Now, when I originally did this problem, I just differentiated both those expressions, made them equal to 0, and actually they share a common root. The derivatives share a common root, which meant I got the right value of k, and I didn't actually have any idea what I was doing with the problem. Now I'm a little bit wiser, a little bit older, and I've done a bit more calc. It makes sense to, when you're talking about the total surface area, to do something like m times the first shape plus n times the second shape, because it's a solid that's made up of a whole heap of different triangles. We don't know how many of each, but that's actually irrelevant. And what we need to do is differentiate this equation. It turns out though, like I said, the derivative of each individual one shares a common root, which means that I got the right answer without realizing it. Okay, so surface area, when we differentiate this formula, we're going to be, I haven't even written the formula down yet. Turns out that the m and the n don't really matter because they're just constants in the front. Okay, let's drag this down to here. Okay, SA differentiated, m stays there, the square root becomes 1/2 in the front, 2k squared minus 2k plus 1 to the power of negative 1/2, then multiply by the inner derivative, 4k minus 2, plus n times root 3 over 2 in the front, multiplied by the derivative of the bracket, 2k minus 1. And like I was saying, I've said it a couple of times, the factor there and the factor there share the same solution, and so we can factor it out. Just to show that, we'll factor it out as 2k minus 1 multiplied by 1 over the square root, which is never 0, multiplied by 2 because it's 4k minus 2, not 2k minus 1. And then the last term just needs an n root 3 over 2. Whoa, why am I factoring out m over 2? Can't do that. There's no m over 2 in the other one. M over 2. That's dodgy as, but it's okay. Okay, so we want to make this equal to 0. So k is equal to 1/2, obviously works. Or the other thing equal to 0, but the bracket doesn't equal 0 for any k because it's strictly positive. The m over 2, m is positive, it's the number of type A triangles. M divided by 2 times 2 divided by a square root, it's all positive, and then the n root 3 over 2 is also positive. So k equals 1/2 is the answer that we want. And it does say that we need to show this value gives a minimum. We could use the first derivative test here or the second derivative test. Personally, I prefer the first derivative test because our first derivative is already messy, and if I want to diff it again, it could be messier. Actually, well, this one's not too bad, but I'd have to use the product rule on the first part. So let's just use the first derivative test. Use the first derivative test. And pick a value of x that's slightly either side of 1/2. We know at 1/2 the surface area derivative is equal to 0. I don't know, pick something like 0.4 and 0.6 and substitute into the surface area equation. As I said, the whole thing here is positive, and then we're just subbing 0.4 into that green bracket. When we do that, 4 times 0.4, 1.6 minus 2 is a negative, and if I sub it into the other green bracket, it's also negative. So we've got a negative slope, and if I do 0.6, I get a positive, and therefore we've got a minimum because we're going downwards and then upwards. Therefore, k equals a half is a minimum. Alrighty, part 3. Find all functions that satisfy this differential equation, then show that these functions also satisfy this other differential equation. Okay, so first up we're solving dy dx equals y to the power of m plus 1. And we're told m is positive. Okay, so it's a separable equation. 1 over y to the m plus 1 equals 1 times dx. If you want dx to have a friend over there and not be lonely, put an integral sign on both sides. Now don't get carried away and go, oh, antidiffs to log. It would only antidiff to log if m was equal to 0, because we'd have 1 over y. But m is positive, so it doesn't anti-differentiate to log. We need to write this as negative m plus 1 to bring it up to the top. Put x plus c. The integral of 1 is x, and then we increase the power here. We've got y to the m, negative m minus 1, be careful with that, plus 1 will just give you y to the negative m divided by negative m equals x plus c, and I can multiply both sides by negative m, and I've got 1 over y to the m equals negative mx plus or minus mc, which we can just call another constant k. Then I can flip this both upside down. Y to the m equals 1 over this stuff, and then power of 1 over m, which is the same as the mth root. So they are the functions. When it says all functions, it's a family of functions there because it depends on m and k. And I don't have any information to be able to find it in the problem. Okay, so that there is my equation. Now, what I want to do is show that it solves the other differential equation. Okay, so this says here, differentiating with respect to x, y to the power of n equals n y to the n plus m. And what they want you to do is fall for a trap here and go, hey, we need to now power this by n. So when we do that, it's going to be still the mth root, but then the stuff's going to be powered by n, or n over m is going to be the power. You write it as n over m there. And now it's asking us to differentiate this. Okay, original problem here says d dx of that equals ny to the n plus m. So we could go and differentiating. D dx of y to the n is the derivative of the stuff on the right hand side. Writing this in red because actually I don't think you should do it this way. But if we do, we're going to drop the n over m down the front and leave the stuff in the middle the same. We're going to write n over m minus 1. And now we need to times by the derivative of the inner function, which is, the inner function there is actually minus mx plus k all to the negative 1 which would diff to minus 1 negative mx plus k to the minus 2, and then multiply by negative m using chain rule. Now the minus m there, running out of colours, the minus m, the minus cancels with that minus, the m cancels with that m. The 1 to the power of n over m minus 1 is redundant, so we end up with n times 1 over negative mx plus k to the n over m minus 1. I was just thinking about whether that needed to be negative or positive power, but it's all I've done is power the 1 at that stage, multiplied by 1 over negative mx plus k all squared. Now I can put those powers together. Because I can add the powers in that denominator. Negative mx plus k to the power of n over m minus 1 plus 2 is n over m plus 1. And what you need to realize is using power rules again, we can write that as negative mx plus k to the n over m and 1 over negative mx plus k to the power of positive 1. That there is y to the n. So because it's in the denominator there, it's actually equal to 1 over y to the n. And then this dude, negative mx plus k, or the 1 over is this dude. So we've got a y to the m and a 1 over y to the n. So we've got equals n times 1 over y to the n times y to the m, which is equal to n times y to the m minus n. Oh gosh, I hope that's right. No, dang it. Y to the n plus m, why is that? Oh, no, the green things are the same, because when we saw it the first time around up here, it's 1 over already. And so, but we don't, it's actually y to the n. My bad, hopefully you spotted that before I did. So that whole thing is actually y to the n. It's not needing to be reciprocated. And that's y to the n plus n. Now, I said that this was all redundant, but this is probably the way that students thought about doing it. They probably go, oh, we've got this function, now we power it by n and differentiate it. I'm sorry for speaking in such a rude tone, but what you would actually do with this, and it makes it a really, really simple problem, is we start off at this y to the n expression. If we're differentiating y to the n using implicit differentiation, that would be n times y to the n minus 1 times dy dx. Now, y to the n minus 1, what is that? Do we even need that? What does dy dx equal? Dy dx was y to the m plus 1. That was the first line of the problem. So if we put that into there, and then add those powers, we hit n plus m, and we're done. And the reason why that's so neat is it actually didn't depend on the original function. We could have solved that problem without anti-diffing properly. It just depends on the differential equation you start with.